Hi all, welcome to the new session. So, in this session we are going to learn the moment of inertia of cylinder and sphere. So, first we will discuss what is the moment of inertia of a cylinder. So, here we are just considering a cylinder, solid cylinder of mass capital M and radius capital R, of mass capital M and radius capital R. So, we are just going to find out the moment of inertia of this cylinder about an axis, about its own axis. So, this is about z axis. So, here also we are imagine that the cylinder is made up of a large number of circular discs of mass small m. So, the cylinder is made up of a large number of circular discs of mass small m. So, the moment of inertia of the cylinder is nothing but the sum of moment of inertia of all such discs. And we have learned that the moment of inertia of the circular disc about an axis perpendicular to its plane and center of mass is given by what? It is m r square by 2. So, the moment of inertia of the circular disc of mass small m and radius capital R is given by small m r square by 2. So, the moment of inertia of the whole cylinder is given by sigma m r square by 2, or it is nothing but capital M r square by 2, capital M r square by 2. So, this is the moment of inertia of the cylinder about its own axis. It is I m r square by 2. The equation, the formula is something similar to the moment of inertia of the circular disc. It is given by m capital R square by 2. Next, we will find out the moment of inertia of the same cylinder about an axis passing through its center and perpendicular to its length. So, this is something tricky. So, we need to find out the moment of inertia of the cylinder about an axis passing through its center and perpendicular to its length. The same cylinder of mass capital M and radius capital R. Here we are considering that cylinder is made up of a large number of circular discs. So, here the length of the cylinder is L, and the radius is capital R. So, we are just considering a small circular disc of thickness dx which is at a distance of x from the axis. Okay. We are just considering a small circular disc of thickness dx and distance x from the axis, and we are just going to find out the moment of inertia of this circular disc about p dash q dash. Okay. Then we will find out the moment of inertia of the same circular disc about the axis p q by using the parallax theorem. Okay. So, first we are just finding out the moment of inertia of this small circular disc about the axis p dash q dash. Here we are imagining that, or we are considering that the mass per unit volume. In the previous cases we considered mass per unit area. Here we are going to consider the mass per unit volume, which is rho, and rho is given by capital M by what? The volume of the cylinder. Volume of the cylinder is given by the surface area, it is pi capital R square into L, or M is given by pi r square L rho, pi r square L rho. So, this is the mass of the cylinder in terms of mass per unit volume. So, if we want to find out the moment of inertia of this circular disc about p dash q dash, we need to find out the mass of that small circular disc. So, it is given by, mass is given by, mass of the disc is given by mass of the disc equal to what? First we need to find out the volume of the disc. What is the volume of the disc? It is pi r square, which is the area into thickness. So, volume is pi r square dx. This is the volume of the disc. So, for finding out the mass of the disk, you have to multiply the volume of the disk with mass per unit volume. So, rho. So, pi r square dx rho will give you the mass of the disk. Now, you know the moment of inertia of the disk about the axis p dash q dash, which is nothing but the diameter. Here p dash q dash is nothing but the diameter of the disk. So, moment of inertia of the disk about the diameter is given by mass into radius square divided by 4. So, I dash moment of inertia of the small disk about the axis p dash q dash, which is given by mass p r square rho dx into radius square r square by 4. So, I dash equal to pi r raised to 4 rho dx by 4. Pi r raised to 4 rho dx by 4. So, this is the moment of inertia of the disk about p dash q dash. We need to find out the moment of inertia of the disk about pq. We can use parallax theorem because we know the moment of inertia of the disk which passes through the center of mass. Now, we need to find out the moment of inertia of the disk about pq, which is at a distance of x. For that, we can use what? Parallax theorem, which is given by I dash moment of inertia of the disk I double dash equal to moment of inertia of the disk about its diameter, which is I dash. We got it as pi r raised to 4 rho dx by 4, pi r raised to 4 rho dx by 4. You can see this one, pi r raised to 4 rho dx by 4 plus mass. What is mass? Mass is what? Pi r square dx, pi r square dx. So, it is given by plus mass into distance square pi r square dx rho, which will give you the mass of the disk into distance square x square, pi r square dx rho into x square. So, this is the moment of inertia of the disk about what? About pq. So, you please understand, first we found out the moment of inertia of this disk about p dash q dash, then by using the parallax theorem we obtained the expression for this disk about pq. Now, we can find out the moment of inertia of the whole cylinder about the axis pq. Just integrate this expression, from the limit minus L by 2 to plus L by 2, or integrate from 0 to L by 2 and multiply it with 2. So, we are just going to find out the moment of inertia of the whole cylinder, which is I, about the axis pq. It is given by 2 into integral 0 to L by 2 what? Pi r raised to 4 rho dx by 4, pi r raised to 4 rho dx by 4 plus pi r square rho x square dx, pi r raised to 4 rho dx by 4 plus pi r square rho x square dx, and there is the term 2, which is given by 2 into, you have to integrate this expression time by time. So, it is first one pi r raised to 4 rho by 4 into x within limit 0 to L by 2, and second one pi r square rho into x cube by 3 within limit 0 to L by 2. So, we can write it is 2 into pi r raised to 4 by 4 rho pi r raised to 4 by 4 rho x within limit 0 to L by 2, next plus 2 pi r square rho x cube by 3 within limit 0 to L by 2. Apply the limits. You have to apply the limits here and rearrange and solve, so that you will get 2 is there. So 2 4 cancel it out, and L by 2 is there. So L by 2. So again pi r raised to 4 by 2 into rho. So here L cube by 8 or L cube by 8 into 3, which is L cube by 24. 2 is there. So 1 by 12. So you will get pi, this pi r raised to 4 L rho by 4 plus pi r raised to 4 L rho by 4 plus, so 2 24 cancel it out, it is 12. So there pi r square L cube rho by 12, pi r square L cube rho by 12. So take the LCM and then solve. You will get it is equal to, and we need to take the term, this one here m is given by pi r square L rho. So we have to take that pi r square L rho outside, pi r square L rho outside. So it is pi r square L rho. Remaining terms here it is r square by 4, here L square by 12, r square by 4 plus L square by 12. So what is this pi r square L rho? It is nothing but the total mass. Here it is the total mass of the cylinder. So it is given by m into r square by 4 plus L square by 12, m into r square by 4 plus L square by 2. So this is the moment of inertia of the cylinder about an axis passing through its center and perpendicular to its length. So it is a little bit lengthy. First you have to consider a circular disc, then you have to find out the moment of inertia of the circular disc about the axis p dash q dash, which is nothing but about its diameter. Then you have to find out the moment of inertia of the circular disc about p q. Then you need to integrate the expression. Okay. Then integrate the expression and rearranging, you will get it is m into r square by 4 into L square by 2. So this is the moment of inertia of the cylinder about two axes. First one about its own axis, it is m r square by 2, and about an axis passing through its center and perpendicular to its length, it is m into r square by 4 plus L square by 2. Okay. So next we will see the moment of inertia of a solid sphere. Before going to sphere, we need to learn another shape, which is the cylindrical shell. So we learned the moment of inertia of a solid cylinder. Here we need to consider the moment of inertia of a cylindrical shell. So it is nothing but it is a hollow cylinder, that is it. Here also we are using the same steps what we have done in the previous case. First one, we need to find out the moment of inertia of the cylindrical shell about its geometrical axis, about its own axis. Here also in the previous case we consider the cylinder is made up of a large number of discs. Here we are just considering the cylindrical shell is made up of a large number of rings, that is the difference. The previous case we consider the cylinder is made up of large number of discs. Here we consider the shell is made up of a large number of rings. Obviously you know what is the answer, moment of inertia of the cylindrical shell about its own axis or about the geometrical axis. Here we consider that the cylindrical shell is made up of a large number of rings, and the moment of inertia of one such ring of mass small m about the axis passing through its center and perpendicular to its plane is given by, it is small m r square. It is small m r square. So it is m r square. So the total moment of inertia of the whole cylindrical shell is given by, it is nothing but sigma m r square, and it is given by capital M, which is the mass of the cylindrical shell, into r square. So, this is the moment of inertia of the cylindrical shell about its own axis. So, in the case of the cylinder, it is m r square by 2. In the case of cylindrical shell, it is m capital R square, which means it is independent of the length of the shell. Okay? It depends only on the radius of the shell. So, second, we are just finding out the amount of inertia of the same cylindrical shell about an axis passing through its center and perpendicular to its length. The same steps. Here also we are just considering a cylindrical shell of length L, radius R. Here instead of the disk, we are considering a ring, or we are just imagining that the cylinder is this shell is made up of a large number of rings. Here we are just considering a ring of thickness dx, which is at a distance of x. Here also the area of the ring, it is 2 pi r dx. It is 2 pi r dx, and the mass of the ring, let sigma be the mass per unit area of the cylindrical shell, and the area of this small ring is given by 2 pi r into dx. So, the mass of this ring is 2 pi r into dx into sigma. Same steps, 2 pi r sigma into dx. Now, you have to find out the moment of inertia of the ring about y dash, which is nothing but the moment of inertia about the ring about its diameter. Then using that expression, you will find out the moment of inertia about y dash by using Parallax's theorem. Okay. So, first we will find out the moment of inertia of the ring about what? Y dash. Same procedure. It is about its diameter. It is given by m r square by 2. Here m is 2 pi r sigma dx, m into r square. What is r? R is nothing but the radius of the ring, which is r, which is capital R, r square by 2, or the moment of inertia of this ring about the axis y dash equal to pi r cube sigma dx, pi r cube sigma dx, pi r cube sigma dx. Then by using the Parallax's theorem, you can find out the moment of inertia of the ring about y dash. Nothing but it is pi r cube sigma dx, pi r cube sigma dx plus pi r cube sigma dx plus mass. It is 2 pi r dx sigma into the distance. The distance is x. It is x square. So, the moment of inertia of the ring about the axis y, which is that is what we require. It is pi r cube sigma dx plus 2 pi r dx sigma x square. Then what we will do next? We need to integrate this expression so that we will arrive at the final expression. So, the same steps you just do, so that we will get I equal to 2 into integral 0 to L by 2, 2 into integral 0 to L by 2. It is pi, just use this formula, pi r cube sigma dx plus 2 pi r dx sigma x square. Okay. Pi r cube sigma dx, pi r cube sigma dx plus pi r cube sigma dx plus 2 pi r sigma x square dx, pi r cube sigma dx plus 2 pi r sigma x square dx. Term by term integrate. So, it is 2 pi r cube sigma x within limit 0 to L by 2, 2 pi r sigma x cube by 3 within limit 0 to L by 2. Same steps, and you have to take m. What is m? M equal to what? M equal to 2 pi r L into sigma. It will give you the mass of the cylindrical shell. So, take that one outside so that you can rearrange the expression, and you will get equal to 2 pi r L sigma Just substitute all this and solve. So, you will arrive at the final expression 2 pi r L sigma into r square by 2 plus r square by 2 plus L square by 12. Similar steps what we have done in the solid cylinder case. So, it is 2 pi r L sigma into r square by 2 plus L square by 12. So, what is this 2 pi r L sigma? It is nothing but the mass of the cylindrical shell, and it is given by m into r square by 2 plus L square by 12. M into r square by 2 plus L square by 12. So, this is the moment of inertia of the cylindrical shell about an axis passing through its center and perpendicular to its length. So, in the case of the solid cylinder also we got m into L square by 12 plus r square by 4. Here we got m into L square by 12 plus r square by 2. So, you need to learn all these things in a very careful manner, because the expressions are somewhat same. So, while doing problems we need to use these formulae. So, just learn all these things in a good manner. So, I am just concluding right now, and we will see the other shapes in our next session. Bye for now. Thank you.